Hi everyone, welcome to chapter 7 of the AI engineering book. This week we are going to talk about fine-tuning. On a high level, what is fine-tuning? Fine-tuning is the process of adapting a model to a specific task by further training the whole model or part of the model. This is different from the other techniques we discussed earlier, such as prompt engineering or RAG. Because for the prompt engineering or RAG, we do not change the model itself. But here for the fine tuning, we would adapt the model by adjusting its weight. So the purpose of doing that is to improve the model's instruction following ability so that it can better fit our need for specific tasks and answering questions and performing tasks in certain domains. However, this benefit does not come for free. Fine-tuning usually requires more upfront investment, such as training the model, and this also requires a lot of the computing resources and talents and time to do that. So this comes with a very important decision point, when to fine-tune and when not to. So there are several cases where it's a very strong case that you should think about fine-tuning. For example, you want the model to generate outputs for specific structures, such as JSON or YAML formats. For the JSON formats, most of the models right now do not have that option, even though the OpenAI API might have that option, but it's not the common industry standard right now. Not to say the other formats such as YAML, which are very commonly used in the software engineering to define some configurations. But in some production cases, if you want to have these outputs always, then you want to have a model that absolutely follows these instructions. Another case is that you want the model to perform better on your specific task. For example, in some very domain-specific areas such as medicine, law, and say education, there are a lot of the domain knowledge where, and also in these cases, if you have your own data, then the fine-tuning model could perform better than just doing prompt engineering or RAG. The third point is to mitigate bias from its training data. So the example covered by the book is that if in the training data for the base model, say have a gender bias for a specific profession, it thinks it's mostly man or woman, which may not be the case or it's outdated information. Then you can fine-tune the model in such a way that the output from the fine-tuned model should reduce these bias. So this is very important when you build customer-facing applications to avoid any kind of bias or other ethics-related answers. And when not to fine-tune. So a fine-tuned model could also degrade its performance for other tasks, even though for the task you want to let it do better, it can improve, but not always. And also, as mentioned earlier, you need upfront investments and also continual maintenance, data, and talents, which basically means in practice, you need a team of engineers, machine learning engineers, and data scientists to maintain the model. So one famous example is Bloomberg GPT, which back in the early 2023, Bloomberg announced that they invest a lot of time and money to build their fine-tuned model that to help their internal analysts and financial professionals to do certain tasks better. But the estimate cost for building that model is several millions of the dollars. But as the book also mentioned, like after several months, with the later version of by OpenAI GPT-4 as well as other open source models, these models actually perform similar or maybe even better results than the fine-tuned Bloomberg GPT on several benchmark results on performing the financial related task. So the point here is that you need to really think about whether it will make the sense or the improved or the future improved performance of the models by Google or OpenAI might do this task as well. Then probably you don't need to fine-tune the models. And also sometimes you can just achieve the better result by prompt engineering, not actually by fine-tuning. So that is also a very common case, I think, especially in the past few years, where people always think about, oh, I need to fine-tune the model. But in the reality is that the base model is getting better almost on a monthly basis. Then what you need is actually to do the prompt engineering better, or maybe some other technique like RAG to give it more examples and data points. So really, you need to think about if fine-tuning is a worthwhile investment for you or for the team. So here is an example when fine-tuning actually helps with optimized token usage when you want to, in a scalable use case, you want to reduce the cost. So how does it work is that in the pre-trained model world, so you provide these common examples, but say there are several hundreds of tokens for these examples, and these are calculated as the cost every time you put into at the prompt. But for the pre-trained model with fine-tuning, these examples are embedded into the fine-tuning parameters and the model in itself. So this way, you do not need to pass in the examples every time. So in practice, this can help the reduce the token usage. I mentioned earlier, RAG sometimes could be a better way than fine-tuning for many tasks. So this raises the question, what is the difference between fine-tuning and RAG, and what is the use case for both? So here is a very good illustration to see how RAG, fine-tuning, and prompt engineering differ and their time capacity. So as you can see on the left bottom for the prompt engineering, you will start with experimenting with the prompt. And then you will add more examples using the techniques we mentioned earlier in the prompt engineering chapter. So here, relatively speaking, is still a lower time involved. However, after adding these examples and engineering of the prompt, you still have not achieved the desired results. So the next logical thing you can do is to consider using RAG. So in the RAG, essentially it's adding more context, such as adding a vector database. So simple retrieval could be just term-based search. So simple retrieval here, just like by the language and the terminology itself to search information. And then the context retrieval could be something with embedding. And with a simple retrieval, if you still think it's not good, and also if it's not conforming to the type of form or behavior you want the model to be, then you can consider about here on the right category about fine-tuning. But Fine-tuning and RAG are not like two totally different things. For some really complex use cases, you can do something like RAG with fine-tuned model. So basically, it means you fine-tune the model, but as mentioned earlier, you need the maintenance, meaning you want the model to always have the latest data and information. So this where RAG with fine-tuned model could be useful, where you have the fine-tuned model that is very specific to your use cases and have the output format and behavior as desired. And you also connect it with a vector database using RAG, where it can also have the facts and information of the latest data. But also that could be also the most complicated thing to do. So one common bottleneck when people fine-tune the model is memory. So because we already, there are a lot of the frameworks and API to train that, to fine-tune the model. So usually it's not about coding or writing the algorithms, but it's more on the hardware aspect of the memory. So that's why in the past, there are a lot of the demand for better GPUs and also all the discussions and excitement around models such as DeepSeek, where you can potentially use a lot less memory than you would expect it to be. So for the fine-tuning as well, there are several contributors to a model's memory footprint during fine-tuning. The first is number of parameters. So usually there are billions of parameters, and there could be even more than that. And also how many trainable parameters, as well as the numerical representations, meaning like how many bits and bytes to represent those parameters. And another common terminology is called quantization, which is the practice of converting a model from a format with more bits to a format with fewer bits. So this is a very effective way to reduce the model's memory footprint. However, also this depends on what you can quantize without hurting the performance too much. So there's always a trade-off on using these techniques. And this can also happen during training or post-training. Yeah, next we talk about some fine-tuning techniques. If we decide that fine-tuning is the right thing, worthwhile investment for us to do. So the commonly used term here is called parameter efficient fine-tuning. And the short abbreviation for that is PEFT. As you see, that PEFT commonly used in the book. So using this technique, we can achieve performance close to that of fine-tuning while using several orders of magnitude fewer trainable parameters. So the context of this parameter efficient fine-tuning basically is that we do not want to do the full fine-tuning, which requires a lot of the memory and computing resources, not efficient and cost-wise to do. So that's why we want to be efficient. And there are two commonly used methods. One is adapter-based, another is soft prompt-based. And the most commonly used technique in the industry is adapter-based by adding additional modules to the model weights. And among these methods, the most commonly used framework is called LoRa, the lower rank adaptation. So this works by adding small trainable low rank matrix to some specific layers instead of updating full parameters. And the way it helps is that it can restrict weight updates to a lower dimensional subspace. And By doing that, it will reduce the redundancy. So we will not go into the details of that. If you are interested, the book has the link to the paper about how these matrix factorization work by adding those low rank matrices and how it will, in practice, be more effective for fine tuning. Another technique is called model merging and multitask. So this visualization here, you can see merging the model is different from ensemble. So you might not be strange with the term with ensemble, which is very commonly used in machine learning world, such as random forest is a type of ensemble model where you will combine and kind of aggregate the results from different tree-based models. So as you can see, basically we'll combine the outputs for different models to get the final output. By merging, we actually mean more on the model inner self. We combine the model into one merged model, and then use that merged model to get the output. So this is also could improve the performance because if we have multiple models deployed, it take a lot of space and the inference time, so it's not optimal. So this way, we should also reduce the cost by reducing the memory footprint by just having one merged model. So there are several practical techniques in terms of fine tuning, and the three most important aspects we need to consider are base model, fine tuning method, and framework. Base model, so usually these are the open source large language foundational models commonly used, such as the Llama model by Meta, as well as the other ones you can find on Hugging Face. So you also need to check out the license, whether it is allowed to do the fine tuning, and also model size will determine the computing resources you would need. And benchmark, as we mentioned earlier in early chapter on evaluation, is that there are a lot of the benchmark websites where you can see how these open source models differ from each other. And there are also different fine tuning basic strategies you can adopt. The two strategies described in the book. So basically, one is to start with a best, strongest model. Another one is maybe you have more data and you start with a weak model. But the core idea is that it's an iterative process, and you need to set up the experiment and the tracking and the benchmark database beforehand so that you can better evaluate and test those models on certain scores. And not just comparing between the fine-tuned models, but also compare that with the base models. Also maybe say with the just proprietary model by GPT-4 or the Gemini model, as well as just with different prompt engineering. Because the ultimate metric is not that we will always want a fine-tuned model, but we want to have the model with the best results on our defined metrics. The fine-tuning method. So usually the recommended method is LoRa, as we mentioned earlier, the low rank method to just change some parameter matrix inside the model and instead of doing a fine tuning. And if not working with some cases, then and you have more resources, and then the full fine tuning could be an option too. And also it will depend on the data volume, how much data you need would also um, have a determination on the method you ultimately want to use. Because if you have lots of data and you do a full fine tuning, you can imagine that will take a lot of time and resources. In terms of framework, usually people will just use the API, such as commonly used by TensorFlow, like PyTorch, where you can easily connect with the data, select the base model, and also have the fine-tuned model by just calling some and functions defined by that API library. So next are the four commonly used hyperparameters. You can kind of fine-tune and changes to see if you can get better result for your fine-tuned model. So it's similar to training the machine learning model training. So the first one is learning rate. This determines how fast model's parameters should change with each learning step. Batch size, examples the model learns from each step to update its weight. Number of epochs, depending how times each training sample is trained on. So the first three are also commonly used hyperparameters in training neural networks. And the last one is more specific to large language model is the prompt loss weight, which determines how much prompts should contribute to this loss compared to the responses. Yeah. Looks like I have some issue with the mic. So if you cannot hear me, just let me know in the chat. Yeah, so here is a key takeaway from this chapter. So really what people need to consider about fine-tuning is more on the high-level strategy instead of the low-level technical details. So the question you need to ask is whether you should or your team should even actually fine-tune model. This you should first ask like whether you have tried out all the fine-tuning or the other methods. Or maybe you can just, if we are using a relatively older model, and then you maybe just want to use a latest version model or different providers, such as if we're using certain model by certain providers that might be cheaper, but not the best performance, then you can try say whether the Gemini, the OpenAI model, more expensive, but whether it can perform better. Because even though it will be, oh, thank you. Yeah, even though if that could cost more by each, say, thousands of token, but still can be much more cost effective for you to fine-tune a model. And the next thing is when you to fine-tune and when to do the RAG. So the key takeaway sentence from that is fine-tune is more about the form or the behavior for the model, and the RAG is more on the context and information, like whether the model needs to know this information to do its task. And in terms of the technique, LoRa, the parameter efficient and data efficient, and also was bimodular. So that's why now people use that as the most common method to do the partial fine-tuning instead of the full fine-tuning. And then lastly, So lastly, the reason we do the fine tuning is that we also need to supply the model with the annotated data. And only the fine tuned model only perform better if we have the high quality data, especially the instruction data. And curating and preparing this high quality and annotated data is the task itself, which is going to be the focus for next chapter on dataset engineering. So in this chapter, it doesn't dive a lot deep into the additional input data for fine tuning, mainly because it focuses more on the high level, whether we should or not do the fine tuning. And the next chapter is more on the data set, which I think is also going to be very helpful, not only for fine tuning, but also to think about the data engineering aspect in the whole AI engineering pipeline. So that's my presentation. Let me stop sharing. Yeah, Arantia, if you have any questions, yeah, feel free to ask or put in the chat. So I think the general trend looks like is when fine tuning is the hottest topic back in the 2023. I remember within the company, we had those AI hackathon event, and lots of the ideas will be surrounding around fine tuning a model with some data set, and there are a lot of the talks and kind of demos, so people fine tune the model on their Jupyter notebook. But then kind of the elephant in the room, people ask questions everyone should ask, but not actually asking is about how to maintain those models, to keep it updated, how to deploy that, so that users can inference these models. So that's why I think lots of the fine-tuned model I see produced by lots of the data scientists or machine learning engineers actually never go into production, because these are all the questions that need a lot of investment and planning. Because if you are just calling the API and you can easily switch to the latest version, and maybe not the ideal or the optimal for the specific task, but it should be performing good enough for most of the tasks. And also, not to mention, is that these models get better quickly, then releasing out more and better versions very frequently. So, if you fine-tune the model, you maybe will spend several weeks or maybe months, and then you need to deploy that and retrain that. It's like a constant consumption for the computing cost. So that's why I think then back in the maybe late 2023 and 24, then people talk about RAG more, the rise of doing more embedding format, because you realize that you just want to provide it as a retrieval for the data point you need. And then maybe in the past 1 year or so, then the latest thing become agent, because you just having a chat box and Q&A is not enough. You want the AI to actually perform, execute the actions on behalf of yourself. But still, I think this chapter is super helpful in terms of understanding fine-tuning. And even though fine-tuning is not like the hottest thing, or not something like people do that commonly, but still, I believe in a lot of the cases, fine-tuning could be very helpful. And also, I think in the future, with the trend is that we are going to have more and more open source models and more adoption of large language models into very specific areas, than having these smaller, cheaper, fine-tuned models for specific tasks could be super helpful. Because one example mentioned in the book is about deploying model onto devices. So like some IoT devices or detached tracks and on the mobile phones. So these cases where maybe the devices might not have access to the internet, and also there's a security requirement sometimes. So, but also, and these tasks could also be very domain specific. Sometimes, say a track need to have those data collected by the sensors and then performing certain tasks. So, which is right now it's very commonly used by about like deploying a machine learning offline model to these devices. But in the future, there could also be a lot of the interesting use cases in these areas to deploy the offline, relatively small, fine-tuned AI models on these devices. Yeah, so I think that's why fine-tuning deserve a kind of chapter in this book, because it will always be one of the methods we can leverage foundation models to kind of better perform our task. Okay, let's see, let me stop recording.